Okay, here we are in chapter 15 for our last section of carbohydrate chemistry. We've already covered a lot of ground here, and hopefully you've been keeping up. This is our last chance to spend some time with the carbohydrates specifically. So by now we've talked about the carbohydrates in general, defined carbohydrates. We looked at some key structural projections like Fisher projections and Haworth structures for the monosaccharides and then the disaccharides. And obviously now it's time to discuss the polysaccharides. So defining polysaccharides, they're polymers of many monosaccharides linked together. They differ in the type of links between monosaccharides and the monosaccharides in the polymer. And they also differ by the amount of branching in the polymer. So we tend to see a few different possibilities to give us distinct polysaccharide structures. If we look here on this slide in particular, we have alpha 1,4 glycosidic bonds to link glucose molecules together in an unbranched chain of amylose. So, of course, not to offend the other polysaccharides out there, but our important polysaccharides include starches made of alpha-D-glucose molecules, amylose and amylopectin. There's also glycogen, which is an animal starch in muscle, which is made of alpha-D-glucose, and then cellulose, which is in plants and wood, which is made of beta-D-glucose. So notice we tend to have glucose as our key monomer in our important polysaccharides. Okay, when we refer to plant starch, we are typically referring to a mix of amylose and amylopectin. So if you look, amylose itself, which makes up about 20% of starch, consists of 250 to 4,000 alpha-D-glucose molecules connected by alpha 1,4 glycosidic bonds in a continuous chain. For that reason, it's sometimes called a straight chain polymer, and it's not truly straight chain because, as you can see here, they're coiled in sort of a helical pattern. Remember that helix when we get to proteins later on. The bulk of plant starch is amylopectin. You see here it's about 80% of plant starch, and it's a branched chain polysaccharide, and it, just like the amylose, it has the alpha 1,4 glycosidic bonds. However, every 25 glucose units or so, there's a branch of glucose molecules attached by an alpha 1,6 glycosidic bond between carbon 1 of the branch and carbon 6 in the main chain, and that's why we get that sort of structure that you see here for the branched amylopectin. Okay, so again, focusing on that amylose in a little more detail, as we said before, it's a polymer of alpha-D-glucose molecules. It's linked by alpha 1,4 glycosidic bonds, and it's a continuous unbranched chain, although it does have that helical twist to it. And amylopectin, of course, is a branched chain polymer of alpha-D-glucose molecules. So amylose and amylopectin both have that alpha-D-glucose as the monomer. Just like amylose, amylopectin also has alpha 1,4 glycosidic bonds between the glucose units, and we can see that the alpha because both OH groups on carbon 1 of the 1 alpha-D-glucose and carbon 4 of its neighbor, they're both alpha. They have the OH groups below the ring, and that's why we get the alpha 1,4 glycosidic bond. But also, as we said before, every so many, roughly 25 glucose units, you also get a branch where you form an alpha 1,6 glycosidic bond to form that branch. So again, it's alpha because the OH group of carbon 1 there is below the plane. On carbon 6, we don't really have any choice but to be above the plane because the carbon itself is above, so its OH group is also above. So the alpha is denoted because of the carbon 1, just like with the alpha 1,4 glycosidic bond. So moving away from the plant starches, which are a combination of amylose and amylopectin, animal starch, or glycogen, as it's more commonly known, is stored in the liver and muscles of animals. So it's hydrolyzed in our cells to maintain glucose and energy levels between meals. This is why, although some of us like to eat constantly, we don't have to, because we do have that ability to store at least some of our glucose in this glycogen form. If we have more glucose, then it goes into fat storage. But the glycogen itself is similar to the amylopectin, but it's more highly branched. So it's very, very highly branched, even more so than that amylopectin. And that's the key structural difference between glycogen or animal starch and plant starch, is that much more highly branched structure to the animal starch. Finally, in addition to being energy storage molecules, we can have polysaccharides that are structural features. So cellulose is a major structural unit of wood and plants. It's a polysaccharide composed of unbranched glucose units in unbranched chains, and it has beta 1,4 glycosidic bonds. We cannot, as humans, digest that beta 1,4 glycosidic bond. We lack the enzyme to break it down. Of course, certain plants and wood itself can be digested by undesirable things like termites, right? We don't like the termites to invade our homes because it's a mostly wood structure, and they do have a way of breaking down that beta 1,4 glycosidic bond, but we as humans cannot break it down, and therefore we cannot use cellulose as an energy source. We can use the regular old plant starches, the amylose and the amylopectin, but we can't use cellulose. We just can't digest it as human beings. Okay, and there we see it, that cellulose polysaccharide is glucose units connected by those beta 1,4 glycosidic bonds, and they're nice, long, straight chains, polymer chains that align nicely with each other and form these beautiful and very structurally sound cellulose structures. However, humans can't digest it because we can't digest that beta 1,4 glycosidic bond, but there are animals like horses, cows, and goats that can get glucose out of this form, out of cellulose in particular, because they have bacteria in their digestive systems that do have the ability to break down those beta 1,4 glycosidic bonds, and that's why you'll often see cows chewing their cud, because they're sending it back down for round 2 with those bacteria. They have multiple chambers to their stomachs, and they're just suited for it. Evolutionarily, they evolved with that bacteria to digest the cellulose, and they can eat things like grasses. Humans, we don't do very well with that because we do not have the enzyme ourselves, nor do we have the bacteria with the ability to break that beta 1,4 glycosidic bond. Okay, we've been through a lot together here in our carbohydrate chapter, and so before we close this chapter, let's have one final learning check. Your task here is to identify the polysaccharides and types of glycosidic bonds in each of the following. So A, there is a picture of cotton, if you can't tell, and B is some potatoes, which we'll take as a example of plant starch. So go ahead, stop the video here while you determine the polysaccharides and types of glycosidic bonds in each, and then start us back up when you're ready to check that work. Okay, and there we have it for A, the cotton, which was on slide 10, so hopefully it was just before the learning check. Hopefully you remembered this one. That's cellulose, which has the beta 1,4 glycosidic bonds. And then B, which was a little while ago when we talked about the plant starch, we said it's amylose, again, in roughly amounts of, say, up to 20% amylose and as much as 80% of amylopectin. The amylose and the amylopectin both have alpha 1,4 glycosidic bonds. So again, the only difference between the amylose and cellulose is the alpha versus beta for the 1,4 glycosidic bond. And then in amylose, or amylopectin rather, we also have that branching that's a result of the alpha 1,6 glycosidic bonds every 25 or so glucose molecules. So there we have it. Hopefully you remembered those names and structure types. If not, it's again more a memorization thing. As you'll see when we get into our other biochemistry chapters, there's a fair deal of memorization. For the organic chemistry content, I try to make it as little memorization possible, as much reasoning and pattern recognition as I can. But for the biological molecules, it's often, unfortunately, a fair deal of memorization. So with memorization, I can't be as helpful, but I certainly would welcome your reaching out to me if you do have some trouble, and we can try to brainstorm together some mnemonics or something to help you memorize those. All right. Otherwise, we are set with chapter 15. Hopefully it went well for you, and hopefully you do reach out to me if it didn't, if there are certain parts that aren't making sense. But otherwise, we'll see each other in chapter 16.